the next part of our modern unit is going to be Debroglie. Louis Debroglie was a French graduate student. He had this crazy idea for his doctoral thesis. It was this: if light can be a particle, can particles like electrons be waves? And they didn't know what to do with this thesis, and so they sent it to Einstein. And Einstein looked at it and said, I don't know if it's true, but it's a good idea. Go ahead and give him his PhD. And they weren't able to prove it for a while, but it turns out that, yes, they can. And how would you prove it? Well, what they did was they found that electrons diffract and interfere. And produce the same type of interference pattern if they're shot at a set of slits. If I take an electron and fire it at a double slit opening, I will still get diffraction interference. So I get central maximum, first order maximum, so on. So, and if it does diffraction interference, if it's acting like a wave, it would have a wavelength. And we can use this same equation that we had for the momentum of a photon to find the wavelength of the electron. So if we have an electron and we have its velocity, we have to find its momentum. So the P equals m times v. Mass of an electron is 9.11 times 10 to the minus 31. And here we have a velocity of 100,000. And that's going to give us a momentum of 9.11 times 10 to the minus 26 kilogram meters per second. Then we can take and plug that in to our momentum wavelength equation, and we get 9.11 times 10 to the minus 26 is 6.63 times 10 to the minus 34th divided by the wavelength. If we do our algebra, plug things in the calculator correctly, we end up with a wavelength of 7.28 times 10 to the minus 9 meters. And if we look that up on the reference table, we find that that wavelength is in X.